All right, I've got a paper here with a claim that sounds, completely out of science fiction. The idea is you can teach a huge, complex AI model how to reason by changing just 13 of its parameters. No, that's not a typo, just 13. So how on earth is that even possible? Let's get into it.
So, we're going to kick things off by treating this whole thing like a puzzle. Because honestly, the main takeaway from this paper, it just feels like an impossible trick that we need to figure out.
Just look at that number for a second. 13. That's it. Researchers from Meta, Cornell, and Carnegie Mellon are saying that's all it took. That's the number of parameters they had to train to get a huge boost in an AI's ability to solve tough math problems. Just 13 little tweaks to teach it a whole new skill? It's wild. And yeah, that brings us right to the big question, the one we're going to try to answer here. How in the world can you actually change the behavior of an AI that has 8 billion different knobs to turn by just fiddling with 13 of them? Seriously, that's like trying to steer a giant aircraft carrier by just tightening one little screw. It just doesn't seem possible. Okay, so to really get why this is such a revolution, we need to take a step back and look at how things used to be done. You know, the old way, because it's that context that makes the number 13 so absolutely mind-blowing. So the best way to picture a large language model is to think of it like a giant control panel, right? And it's got billions of these tiny interconnected knobs. Every single parameter is one of those knobs. And for the longest time, training or fine-tuning the AI meant you had to go in and painstakingly tweak massive groups of these knobs, just trying to get the output you wanted. And this table here, it really lays out the scale of what we're talking about. You've got full fine-tuning. That's the old school, brute force way, adjusting all 8 billion knobs. Then something much better came along called LoRa. This was way more efficient, kind of like just adjusting a few key sections of the control panel, but you were still messing with millions of parameters. And then you have tiny LoRa, the new method from this paper. And that's like finding out this whole gigantic control panel can be controlled by a few secret master knobs. That's the incredible jump in efficiency we're looking at. So, the big question is, how did they find these master knobs? Well, that brings us right to the breakthrough method these researchers came up with. They call it Tiny LoRa. All right, first, let's quickly cover the foundation this is all built on. LoRa, which stands for low rank adaptation, was already a huge improvement. The big idea was, instead of messing with the original knobs, you cleverly bolt on a small new set of controls. They're called adapter matrices. These could change the model's behavior, and it slashed the number of parameters you had to train from billions all the way down to millions. A pretty big deal. Then came the next step in the evolution, LoRa XS. And this is where things get really interesting, because it made a critical change in thinking. Instead of adding new controls, it started asking a different question. What if we could just learn to better recombine the most important settings the model already has? That was a huge insight, right? The power's already in there. You just have to figure out how to conduct the orchestra. And that finally brings us to Tiny LoRa. This is the really radical idea. It takes that whole recombination concept and pushes it to the absolute extreme. It figures out how to learn a single tiny little vector. We're talking sometimes just one number that acts like the master controller for putting together all those powerful, pre-existing abilities inside the model. So how does this actually work in practice? Well, it's basically a 4-step recipe. First, you look inside the AI and find its most powerful, most important settings. Second, you create that tiny, trainable vector, and that's where our 13 parameters live. Third, you use a fixed random matrix to kind of blow up that tiny vector into a full-sized instruction sheet. And finally, number 4, you use that instruction sheet to tell the model exactly how to mix and match its existing skills to solve the new problem. But, just coming up with the method is only half the story. The other, maybe more important half, is why it works so ridiculously well. And the secret ingredient, as it turns out, isn't just about how you teach the AI, it's about the whole philosophy of the lesson itself. Okay, these two charts right here, this is the absolute heart of the paper. On the left, you've got reinforcement learning, or RL. On the right, supervised fine-tuning, SFT. Now look at the bottom axis. That's the number of parameters we're training. See that chart on the left? With RL, performance just rockets up to over 90% with just a tiny handful of parameters. Now look at the one on the right, SFT. You need hundreds of thousands, maybe even millions of parameters to even get in the same ballpark. It's a night and day difference. So, what is the big difference here? Well, think of it like this. Reinforcement learning is like teaching a dog a trick. You just give it a simple reward signal. Good dog if it gets it right. Nope, try again if it's wrong. The AI tries to solve a problem, and all it gets is a thumbs up or a thumbs down on the final answer. The signal is simple, but it's super clean. Supervised fine-tuning, though, that's more like forcing the AI to copy your homework word for word. It has to memorize every single step, including your specific writing style, your phrasing, all the junk that doesn't actually matter for the answer. So the signal is dense, sure, but it's also incredibly noisy. And the researchers themselves put it perfectly. They basically say that with SFT, the model gets confused. It can't tell the difference between the important logical steps and all the stylistic fluff. So it wastes its very limited learning budget on both. But with RL, all that noise is gone. It gets a pure, clean signal about the one thing that actually matters. Did you get the right answer? All right, so this is a really cool technical trick. No doubt about it. But so what? What does this actually mean for the real world? Why should you and I care about this kind of extreme efficiency? Now check this out. Because this chart shows something that is completely counterintuitive. I mean, you would think a bigger, more complex AI would need more tweaking to learn something new, right? But what this research found is the complete opposite. As the base model gets bigger, that's the bottom axis, the number of parameters you need to teach it something new actually goes down dramatically. It turns out bigger models are somehow easier to program with these tiny little updates. It's wild. So what does this mean in the real world? Well, this level of efficiency is a total game changer. We're talking about radically lower costs for training. It paints a picture of a future where one server could host thousands of different personalized AI models, one for every single user, because each personality is just this tiny little file. This could also be a huge step in solving catastrophic forgetting, where AIs forget old skills when they learn new ones. And ultimately, it just makes powerful AI customization accessible to way more people. Okay, and that brings us to our final thought. Let's zoom out from all the technical stuff for a second, because this research really forces us to ask a much bigger, more fundamental question. And his quote from the paper is the perfect place to leave things. Think about it. How is it even possible to learn a complex skill like mathematical reasoning in just 13 parameters? Well, the authors float this mind-bending idea. Maybe the model isn't learning the knowledge at all. Maybe the knowledge to solve the problem is already in there, buried deep inside its billions of parameters from the get-go. And maybe this whole fine-tuning process isn't about teaching it what to do, but just changing its style. Maybe it's just nudging it to give longer, more step-by-step answers, which in turn unlocks a reasoning ability it had all along. So I'll leave you with this question. What does it really mean for an AI to learn something new?